So this is the second hour of Physics 1617 for Monday, April 20th. In this section, we're still talking about circular motion and centripetal acceleration, and we want to talk about this particular problem here. This type of problem is a pretty classic, physics problem for circular motion. You'll see this in a lot of textbooks, something like this. It says mountain roads are tilted or banked so that even if it were covered with ice, a car can make a horizontal circular turn without sliding off the road. If you think about your experience driving in the mountains, like out east of town, or if your family's ever gone on a trip or anything like that, where when you're driving on these mountain roads, quite often the roads are kind of banked inwards so that it can kind of help you make the turn. I think even really like exit ramps on a lot of roads, like here in Los Angeles, are banked as well, where you have this situation where you've got like a turn, but there's this gradual kind of, if the car is moving into the screen, then there's this kind of gradual. Here, I'm drawing this very badly. Suppose that you've got a car, and these are the wheels down here, and you're looking at it from behind. So here's your car, and here's the back of the car. It's really boxed. So here's the back windshield, right? And there's the taillights here and here. So this is like a banked road, okay? You guys all driven on roads like this before? Or ridden in a car when you're on a road like this where the car's going into the board, but it's turning, to the right. Okay, so these type of banked roads can basically make it easier for the car to make the turn. NASCAR and a lot of racetracks are also set up in just the same way in order to allow the cars to travel faster as they make the turns. And this problem is about that, okay? So the basic idea is you've got this banked road, and it's banked at an angle, banked at an angle theta down here. Okay, there's an angle theta right here, right? It says a car can make a horizontal circular turn without sliding off the road if the car is traveling at the right speed. We want to find an expression for the banking angle theta for a car traveling at speed v, making a turn of radius r, okay? An expression for the angle theta for a car traveling at speed v and making a turn of radius r, okay? And it says specifically so that even if they were covered with ice, and the fact that the ice here is here, we're going to basically assume that this road we're driving on is frictionless. Which means that if there was no velocity, the car would tend to basically just slide down the road like this, okay? It would just slide without any speed. Its weight would just carry it down the ramp, right? Because it's a frictionless surface. All right. So we've got this banked turn, and I really don't know the best way to draw it. I hope you guys in your brain already have a good idea of what this looks like, but this is the way that I think about it. Your banked turn is something like this. You've got this kind of, imagine like a circular track that's shaped kind of like a bowl. Oh my god, this looks so bad. Maybe if I erase the part in the front, like that. You've got this circular track, right? And let me draw kind of at least a dashed line here to represent this kind of circular. And your car is traveling basically like here. So this is where the car is. And we can label some of the stuff of what's going on here. So the car is going around in a circle, okay? It's banked like this. It's like a bowl. So imagine a bowl. And the car is driving around the inside of it. The banking angle is down here. It's theta. And the velocity of the car is v. And then the radius of the turn, okay, is going to be out to here. That's going to be the radius r. Okay? Go from the center of the car out to here. And we want to relate all these things to each other. Okay? So how do we do that? For our car, we can identify the forces that are acting on it. Can you guys tell me, what would the forces acting on this car be in this case? Yep, and the normal force points which way? Like, kind of like perpendicular to the, so, like that. And then what else is there? Weight. Yep, there's a weight, W. What else? What else is there? Anything else that you guys can think of? Okay, and again, just to relate this back to what we said earlier, if you think in your brain that there's a force that pushes this way, I don't blame you. But is there a force that goes this way? No, there's not. This is not a real force. Sometimes referred to as a pseudoforce. Friction would be there, by the way, Ash. We're going to say it's frictionless, but if there was friction, I guess you can think for yourself what way it would go. Maybe we'll talk about that at the end of that, but maybe we'll add friction in later and see what happens. But over here on the left, there is no force that points to the left. But I will say this. Imagine that you are in a car and you're turning along one of these turns right here, right? You're turning to the right, right? What direction does your body go if you turn to the right? Oh, I see a lot of questions I need to answer. Sorry, go ahead. What direction would your body go as you turn? You feel your body go to the pseudoforce one. Yeah, left, right. So, what is it that's actually making your body move left? Yeah, inertia, exactly. Your body wants to go in a straight line, yeah, and your inertia carries you that way. That's it. So that force you feel it's sometimes referred to as an inertial force. I don't like that kind of language, but I'm just a physics teacher. I'm sure there are a lot of systems in which it makes sense to describe it. I think from what I've seen, when you describe things like hurricanes and stuff like that, you do have to kind of consider these pseudo forces if you really want to describe what they are. But just so you guys know, a pseudo force or a fake force is a force that appears when you are in a system where you're accelerating, okay? Think about the following scenario. You're in an elevator, right? The elevator starts to accelerate upwards. You feel a force. It feels like you're being pushed down, right? You guys know what I'm talking about? You're in an elevator. You're on the bottom floor and you're going to the top floor. Right when that elevator starts to accelerate, it almost feels like you're pushed downwards, doesn't it? But really what you're feeling is the ground pushing up on you, and you're in a non-inertial reference frame. You're in an accelerated reference frame. And the effect of that is, you feel a pseudoforce. When you turn to the right, you feel this fake force that pushes you to the left. It's not a real force. It's inertia. It's inertia. You want to go... Anyway, so I'm kind of beating the dead horse here. I think you guys get the idea, I hope. So those are the only two forces that we have here. In addition to those two forces, there's also going to be an acceleration. That's not a force, obviously, but that acceleration is going to point towards the center of the circular motion. And this object, this car is basically going around in circles, right? It's traveling around in a circle like this as it goes along a turn. And those are all the forces that we have. Okay. Right. So here's the thing. How do I want to orient my coordinate system now? I have to pick a radial direction, and I have to pick a positive y direction, okay? Do I want to make my radial direction point this way, or do I want to make my radial direction point this way? Along the acceleration. Yeah, exactly. You need to make it the same direction as the acceleration. So the radial direction, this is one of our rules, right? If you can, you always want to make the direction of the acceleration the same as the direction of one of your axes, right? That way, you only get acceleration along that one axis. So even though back when we did problems with objects on planes, we would always make it so that the x direction would point like this, the reason why we don't do that here is because the acceleration doesn't point along the ramp anymore. It points in the same direction as, toward the center of the circle. Okay? Now that we've got that, let's redraw our free body diagram over here so we can actually draw some things on it. So we had our normal force going this way, and we had our weight coming down this way. That line is actually much more straight than usual. And then I would say that based on the angles in the problem, we know we're making our axes like this and like this, so that's y, and that's plus r. Now where does the angle show up? I think it's going to show up right here, right? Yeah, definitely. Theta... 90 minus theta, yeah, this is going to be the angle here. And then we can break up that normal force into a component that goes this way, and a component that goes this way. This side will be in cos theta. This side will be in sine theta. And then I've got our acceleration vector that goes this way. And we'll say... Net force in the y direction in this case is going to be equal to may. And then net force in the radial direction is going to be equal to m times the acceleration in the radial direction. In the y direction, its y coordinate in this case is going to stay constant as it moves along this path. So this is going to be 0. It's not going to slide up or down. So in the y direction, we end up having just n cos theta minus mg is equal to 0. And then in the radial direction, we've got... No, it will be. I'll put that in there in the next line. I'm just going one step at a time. The mv squared over r. So net force in the radial direction, there's only one force, right? Which is n sine theta. And that one's going to be equal to mass times radial acceleration. But the radial acceleration is always just going to be mv squared over r. So we need to combine these two equations together. You'll notice that this problem, even though it's about a car driving along an icy road, it has equations that are pretty similar to what we got before, right? And if we solve these, we're going to get exactly the same answer as we got before. These problems tend to be very, very repetitive in terms of the kind of things you see show up in them. You plug this in for n, and you end up getting the same thing we got before. You end up getting g tan theta is equal to v squared divided by r, which means that tan theta is equal to v squared over rg. Actually, exactly the same answer as we got before. It's very common that that happens in these kind of problems. You guys have any questions? We'll solve what the angle theta will be for the next problem. Oh, here we go. Oh, there's some other questions I want to answer too. Some questions about labs. If the acceleration has an x and y component, does positive x and y have to correspond? Yes. You saw people doing the opposite in your lab and your homework to success. It's probably because they're like doing something wrong twice. Does that make sense? You do have to do that. Now, I'm being a little bit what's the word for it? Like dogmatic, maybe? Like, in terms of, yes, I know very well that there are other ways to do things. Can I ask, Ash, the people you were talking about, did they make it so that one of those accelerations was negative or something? Was there like an... They did what I said? Did they suddenly make one of the accelerations? Okay. I can only assume. I'd have to go look exactly at the work. Okay, well, quite often when people do stuff like that, sometimes it can work. Okay, sometimes it can work as long as you're really careful. But you just have to be really careful, Ash. What I always like to teach is a method that will work 100% of the time, a method that I can replicate and describe over and over again in the same way, so that each time if you ask me, I'm always giving you the same answer, maybe in a different way, but that way there's no inconsistency, right? But like, for example, are you talking about this problem? Oh yeah, you're definitely talking about these problems about electricity. No, were you talking about this problem, Ash? Yeah, so I was describing this to someone earlier, and you can eventually prove that you get accelerations that look something like this. This is the acceleration for the object, and what I said was you want to make, since the y component of the acceleration goes down, you want to make this positive y, and you have to make this positive x because you have a in this direction and a cos theta back in that direction, which a cos theta is guaranteed to be less than a, right? So positive x has to then go this way. Does that clarify, Ash? Like, this is how I would do it, okay? But, it's possible that you could turn this around and you could take this and put it up here for positive y, and it might not make that much of a difference, right? You probably can, because there's, I think, only like one force that points in this direction or something, right? No, there's more than one. Yeah, I wouldn't recommend it, Just saying. Like, you can. I just wouldn't recommend it, personally, from my experience of doing these problems. You may be able to get the math to work out, but I don't know. So, yeah. If other people are being successful without using that method, Ash, I would say that's cool. Just be careful. You know, that's all I'm saying. All right. Okay, you guys asked about friction with this problem. Do we want to talk about that? What would happen if I had friction here? What? Oh, wait a second. What'd you say, Ash? I saw that question. I thought I'd answered it. I'll answer it again. Just, yeah. So her question was, can you make positive y the other way? You can. You're welcome to try it. I don't know that it will work out. It might work out. I don't know. Okay. So friction for this problem. Maybe we do the next one and then we add in friction at the end now that we have numbers. Let's try that. Because the next problem is basically an application of this. Of what we just did. This one actually is a picture too. I probably should have brought that one down there. So cut. Go down here. Paste. Alright, there we go. So this one has friction, okay? Alright, so it says, a mountain road has a turn radius of 500 feet and is banked for a speed of 330 miles per hour, okay? If fast Florence takes this turn at 60 miles an hour, find the minimum coefficient of friction such that her car does not slip. I think this one is modeled off of a problem from university physics. I'm pretty sure that there's a really similar problem. I don't know if I assigned it, but I know there's a problem in your book that's a lot like this. Okay, now we've got this answer from before that we're going to use, so I'll go up a little bit. This is what we found in the last problem, right? The relationship between theta, v, and rg, right? And in this problem, they're telling us that we have a radius of 500 feet. So let's go ahead and write that down. R is equal to 500 feet. We have a speed of 30 miles an hour. So that's our velocity, 30 miles an hour. Okay. And it says that it's banked for that speed, right? And this problem is supposed to be taken kind of in concert with this one. Right, so this one, if we read it again, example 4 said, mountain roads are tilted / banked so that even if it were covered with ice, a car can make this turn, right? So what we need to do first is figure out what the angle is based on this information here, right? We know from the previous part that this is how they're related to each other, so we should be able to state that, go back down just a little bit here, that if I take the arctangent of v squared over rg, that should give me what the angle is. Now I can't immediately just put these numbers into here. I need to do some conversions, right? So we need to get 30 miles an hour needs to be turned into feet per second or to meters per second. So 30 miles per hour, if we, here, let me write it as an actual ratio. So that's 30 miles divided by 1 hour. And we can go to feet per second. We can replace the hour. If we say 1 hour is the same thing as 3,600 seconds, that ratio is equal to 1, so it doesn't change anything we multiply by it. And then to get rid of miles, we can say 1 mile. I think this is right. It's 5,280 feet. Does that look right to you guys? Feel free, someone, if you want to look that up on the internet or in your book. I don't have my book with me to make sure that that conversion's right. And that's going to give us, let's see, where's my calculator? Oh, we could if you want to, but I mean, we don't have to, right? I'm going to use this G, though. I'm going to use that G. Okay. Oh, this is tan inverse. My bad. This should be tan inverse. That's 44 feet per second. We've got feet for R, and we can put G in 32 feet per second squared, and that should allow us to find theta. So we'll get theta is equal to the arctan of 44 squared And I'll have you guys calculate this. Why don't you guys tell me what that's equal to? So I got 6.9 degrees. Yep. It's like 6.899, right? Just call it 6.9. Now that's just the beginning of the problem. We now know what the banking angle is, right? Because it said it's banked. Let me erase some of the strokes that I put in here. It's banked for that speed, right? It's designed so that you could make this turn around this mountain, going at 30 feet per second or 30 miles an hour, which turns out to be 44 feet per second, without slipping. That means you won't slide up, you won't slide down. You'll just easily take the turn, right? Does that make sense? So we know the angle, and then it says if fast Florence takes this current at 60 miles an hour, find the minimum coefficient of friction so that the car does not slip. Okay? So same problem. We've got our ramp. We've got our car. Okay, I'm just going to use a little dot to represent our car right here. We know the forces on the car too. One of them was the normal force that goes this way, right? And the other one was a weight vector that goes down this way. Ooh, that's nice and straight. Now the question is, if this person tries to drive at 60 miles an hour, what's going to happen to the car if there's not enough friction? Is the car going to slide up the ramp, or is the car going to tend to slide down the ramp? Yeah, if you go too fast, the car is going to be carried upwards by its inertia, right? So what direction should the friction force be in that case? And we're going to call it static friction because we want the car wheels, basically, we don't want it to move this way and we don't want it to move that way. We just want it to stay in place, okay? We want the wheels to stay in place, so we'll call that static friction. All right? Okay, so this is our scenario now, and we need to also identify on our picture what the direction of the acceleration is, and I would say that our acceleration vector is going to be pointing towards the center of the circle here. So in keeping with what we did before, we'll make that the positive radial direction. And we'll make this direction the positive r direction. And we'll break up our vectors accordingly. Does that make sense to you guys? Oh, why? Thank you, sorry about that. That's why. There you go. Yeah, the direction of friction. The idea with the friction here would be that if the car goes faster than the road is designed for, the tendency is going to be for the car to want to kind of slide up the ramp. If the car was moving too slowly, maybe this is more easy to understand. If the car was moving too slowly, it would just slide down the ramp, basically. Without enough velocity. Explain why it's static. As long as it doesn't slide left or right, it's static friction, basically. As long as it doesn't slide up or down, it has to be static. Is the car turning left? In this picture, yes, the car is turning left. That's right. And it's turning left, the natural inertia of the car wants to force it to go to the right. Because it's turning left, that means that its inertia tends to make it want to stay in a straight line, right? Which means it's going to tend to want to slide up the ramp. Up the ramp would be, forwards, right? Consider this. Maybe I can draw kind of you have a turn that goes like this, right? And I've got a car, and the car is moving along like this, right? It's turning to the left, right? It's turning to the left, but the natural tendency of the car would be to move this way, right? Does that make sense? This would be the inertial kind of tendency to move in a straight line. But the car instead is turning left. Oh, it looks bad. And so that's why, as it turns left, it's going to tend to move up to the right if it goes faster and faster and faster. Does that make sense? Spend some time thinking about it, Koa, and it's okay if it doesn't immediately make sense to you. You do have to spend some time yourself thinking about it. Can we rotate the r-axis to align with the road and make the y-axis perpendicular to the road? You can. It will create components for the acceleration. And I don't want to do that, the Physicsinator. You can try it yourself. It'll be a little more work. You'll get the same answer we get. But, yeah. Also, the friction needs to be this way just to prevent the car from sliding away. How else could I can think of other ways to describe this. I hope this makes sense to you guys. Okay. Did what I say answer your question, the Physicsinator? Why it is that I would want to... Okay. We want to simplify the math as much as we possibly can. That's really the reason why. You can make the axes point however you want to. You can also make the axes so that they're not perpendicular to each other. It's up to you. Okay, so this picture is going to get a little more complicated now. In fact, I kind of want to make it bigger so that we can actually draw what's going to happen now. So those are our axes, right? Which means for each one of our forces now, we need to break them up into components. So let's do that. Now, where's our angle theta? Here, let's draw some other lines in here so we can talk about the angle theta. So this angle here is theta, which means that if I draw a line to represent my radial direction here, that if that's theta, then this angle right here is theta as well, and you should be able to prove to yourself that this angle is theta. And then you should be able to say that the force here can be broken up into a component that goes this way. Sorry, a component that goes up. And a component that goes left. Oh, sorry, this is going to be the n sine theta. And then this one will be n cos theta. And then on Fs, we'll break that one up like this. And like this. Okay. Oh god, those aren't normal forces. Oops. It's the friction force, my bad. I'm just going to call it F too, because I don't want to... This is going to be F sine theta. And then this one's going to be F cos theta. There's a lot more forces when you put friction in, right? I mean, the problem immediately gets more complicated. All right. So now what we're going to do, just like we did before, we say net force acting in the y direction has to be equal to 0, because the idea is the object, we don't want it to slide up or down. And we also want to say the net force acting in the radial direction is going to be equal to the mass of the object times its radial acceleration, which is the centripetal acceleration. In the y direction, we're going to have just two forces, I think. No, three forces. There's n cos theta minus the 2 going down, so minus mg, and then minus f sine theta. And then in the other direction, in the radial direction, oh, this is going to be equal to 0. In the radial direction, we've got two forces. There's the n sine theta component, and then plus f cos theta. And that's going to be equal to mass times velocity squared divided by the radius of motion. And those are the two equations we need to solve, along with the fact that the static friction force is going to be equal to the coefficient of friction multiplied by the normal force. And ultimately, this is what we're trying to find, right? Is what is mu equal to? Go back to the question so we can understand what we're doing again, right? if this person takes the turn at 60 miles an hour, find the minimum coefficient of friction that the car does not slip. Does not slip means it doesn't slide up, it doesn't slide down. All right, are you guys ready to solve these equations? Do you have any questions?
So we're using the maximum static friction.
Mm-hmm. Yeah. It's kind of a weird thing to say, but to get the minimum coefficient of friction, we still want to deal with the maximum friction force, if that makes any sense. Because, like, it's the speed that's going to make it so that the car tends to go up, but you want it to stay still, so really you want to figure out the friction coefficient needed to make it just be on the verge of slipping, which is why you want to be looking for the, FS max, basically. Any other questions before we solve this? So here's what I'm going to do. I'm going to say that we replace F here with mu times N. And then I'm going to move the mg to the right-hand side. We'll do the same thing, this equation over here. This one's going to become n sine theta plus mu times n times cos theta. And that's going to be equal to mv squared over r. And then now we just want to go about solving. Our goal is to find theta. Does everything look right there? Did I make a mistake? So what we'll do next is we'll factor the n out. Why did I say theta? I'm so sorry. We're looking for mu. My bad. We know what theta is. This is theta. Yeah, we're solving for mu now. So we need to eliminate n. This is going to be quite a bit of algebra here. I'm going to have to scroll down too. So we can, what's the easiest way to do that? I can solve one for n and plug it into the other one. I could divide these two equations by each other. So like if I did 1 and 2, I could say that basically, which one do I want on top? I want 2 over 1. If I take equation number 2 and I divide by equation number 1, I would say that we're going to get the n's to cancel out and the m's to cancel out. So we're going to get something like this. So equation number 2 divided by equation 1, the normal forces will cancel out. And now we just need to isolate mu, which is kind of annoying, honestly, but we'll isolate it out of here. So we'll do that by multiplying this one to the right-hand side. So we end up getting here. I'm gonna multiply this out. So it's gonna be times cos theta here minus and now we need to get mu's together. That's going to be something like this. I'm going to stop for a second. You guys check. See if that algebra makes sense to you. I'm just looking back. I feel like I had to have made a mistake here. It's just too many steps. Kind of looks right, though. And now, in order to just kind of keep things simple here, let's remember that v was equal to 60 miles per hour, which we need to multiply by... you know what? This is easy. I'm pretty sure it's 88 miles, because we said that, I think 30 miles an hour was, what was it, 44 feet per second? So obviously 60 miles an hour has to be double that, right? Save ourselves having to do a conversion again. And then, what else do we need? We knew R, I think was 500 feet. And obviously G is, we're going to use the feet per second version, which is 32. So now we just want to solve for mu. I think we're going to get something like mu times. The angle theta was 6.9 degrees. So what I'm going to do is just calculate everything in these parentheses here. So that's going to be plugging in the numbers. You're going to get cosine 6.9 plus 88 squared divided by... This is something where I feel like I need to be doing this like on screen. I don't want to... It's just too many things I'm plugging in. So let's do that real quick. Second to load. I don't know why it takes so long to load this. There it goes. Okay. So, left-hand side. This equation here, we're doing, put this in degrees. So it's the cosine of 6.9 degrees plus v squared, so that's, oops, 88 squared divided by RG, so divide by 500, and then we also need to divide by 32, and then that's multiplied times the sine of 6.9. I want you guys to calculate this too, just in case I make a mistake. So this is 1.051. And then on the right-hand side, we're doing 88 squared divided by 500 divided by 32 times cosine 6.9, and then minus the sine of 6.9. So the right-hand side ends up being 0.36, which means that mu is equal to, and now we can just take our answers. It's basically equal to this divided by this. So 0.343. That's the minimum coefficient of static friction to prevent the car from sliding up the ramp. Okay. I hope that made some kind of sense. Do you guys have any questions? Does that all make sense? Problems like this, the algebra is like, there's just so much of it that I feel like you get lost in what we're actually doing, right? Because in reality, the vast majority of what we did for work-wise came from analyzing all these forces in this thing right here. And then we got these two equations here. And from that point, it was really just a matter from this point forward of just finding the missing information, you know? So there you have it. The only other unknown here would be the normal force N, which we could calculate if we want to from either of these equations. All right, did I lose you guys? You've had enough algebra maybe for a little bit? Okay. Maybe Daniel has a question. I'll wait a second. Still here. Haven't walked away from your screen yet? All right. So what I'm gonna do is we'll take a break right now until like 4:05. So like an 8-minute break till 4:05, and then I'm also gonna actually we'll take a break till 4:10. So we're gonna 12-minute break, and I'm also gonna answer now after I stop the recording.